Next speaker is Thomas Angelini from Harvard University, speaking on multi-cellular substrate deformation guides guiding collective migration.
Yeah, you still need this? Yes, I do. Thank you. I'll give it back to you in a minute.
Okay. Is this working? No? Not yet? Maybe it's just a button or something. Oh, mute. Is this it's okay? Okay. Hi, I'm Tommy Angelini from the Weights Lab at Harvard, and I think really the theme of this talk is just it's like we've heard about a few times today. Basically, mechanical communication for guiding collective motion, and I think it's along the same kind of lines as what Cindy talked about and what Paul talked about. But I think the mechanism here is something totally different. So we've heard about the importance of tissue cell collective migration. I won't go into it after all morning. I guess what I want to say is that these cells, of course, are self-driven, but their interactions are adhesive. And in my case, probably, well, one of the most important attributes is that they're interacting with this elastic medium. And so the experiment is we have a huge island of cells, and we look at a small region near the middle, far from the edge, and just ask, how do groups of cells inside of here move? Do we see any collective motion? Do they move in small groups, big groups, etc.? And as you pack them more and more together, do these correlated domains grow or shrink or what? And so, if from Cindy's talk, we might think, well, her nice paper suggests that a cell contracting here and a cell contracting here feel each other through this transmission of stress to the substrate, right? But as I think has been discussed, if you glue these two cells together by the cell body, you can get rid of that vector there and balance the forces. And that gives you a way to, say, deform the surface over a longer distance, and forces transmitted from cell to cell. And in fact, Javier Tripod from the Fredberg lab, I think, showed this quite nicely, that the forces transmit across the entire colony, and that, on average, this thing acts like one giant contracting unit. However, which isn't part of my work, there are fluctuations in there, and the fluctuations, I think, are what guide motion inside of here. Oh, and if I could just make one comment, I think that we've heard lots of nice models of hydrodynamics and particles colliding. I think this particular case, the most I think pertinent adaptation of a good classical model would be an active version of the Frankel-Kontarova model, where your cells, say the springs and balls, are active, you have damping, but also they can somehow remodel the potential they see. So that would be a new version. And in fact, what I think is that they're deforming the surface, creating what is effectively a potential that changes, and then therefore changes how they move. So, okay, just to get to it. This is a movie, just a sample of data that we would see. They're MDCK epithelial cells. It's about an 800 micron field of view. We take 16 of these data sets in succession to get many density points. And so you start off at low densities and go to high densities. And this is how they move together. If you look at how they deform the substrate below, you see little teeny fluctuations. It's like little blades of grass blowing in the wind or something. It's I don't know, it doesn't look all that dramatic, right? But as we've learned, you have to relax the cells, or kill them, or remove them from the surface. So if you trypsinize the cells, instead of that little short wavelength high frequency motion, you see larger scale deformations. Again, this is the same 800 micron field of view, so you see like big bands that move in the same direction. So there are large scale deformations that propagate from cell to cell and actually move in the same direction. These deformations are no longer balanced within the cell. They're balanced over many cells.
What was the cells?
I'm sorry?
You said that you removed the cells.
Yeah, we trypsinized them.
What correct motion?
So this is a comparison of a time point at which you have cells on the surface, and then to the same place where you've removed the cells. And I'm just flashing back and forth between those two. Yeah. So the motion never actually looks like this. This is just revealing what's hidden underneath. Yeah. So if you do PIV on those kinds of, if you compare those two fields of view and do PIV, same 800 micron field of view, you do see indeed large scale collective deformations below the cell layer. So to get a length scale out of this, we just calculated a correlation function, something similar to what we heard about yesterday, and we take a displacement at one point and dot it with a displacement some distance r away, and then you average this over all orientations and over all times throughout the data set, and that gives you a 2-point correlation function that's sensitive to changes in orientation and displacement. And in that case, we see this correlation function decays exponentially, and you can just fit a line to this and get a correlation length. And what we see is as the experiment goes on and cell density goes up, this correlation length grows. So somehow the correlated domains of deformation are going up. And so just to show you a quick kind of flavor of how the cells move, at low densities, their shape is irregular. They're quite violent. They're moving fast. But then at later times, the motion is much more smooth. You start to see more like streams and less kind of violent behavior, but more streaming, smooth behavior. And eventually, you just see lots of big groups of cells that move together. So you can do the same PIV analysis on that motion, and indeed, again, you see large swirly domains, and we use almost the exact same correlation function, but now on velocity vectors. And this time, instead of decaying exponentially, we see it at each time point we have a negative minimum, which means these are more swirly. And so we take this negative minimum as to be basically if you have a velocity vector here and you look some distance away, they're going in the opposite direction here, and that defines kind of a domain over which they can move together. And so you can see that correlation length grows as well in time, whether you plot it in microns or in units of cell lengths, say. So how are these patterns related? You can overlay the two PIV movies and stare at it for days, which I did, and I couldn't figure anything out. So, instead, why not just plot, say, the correlation length of deformations versus the swirl size? And so, of course, they both grow in time, so they're going to both grow with one another. And they're of the same order. They're quite close in magnitude. So that's our first clue that the deformations are somehow guiding the motion of the cells. Secondly, if you do the same experiment on glass, you can't see there's no deformations in the glass, but you can still get a swirl pattern on glass. And what we find is that the swirl size actually decreases with density on glass, where it increases with density on polyacrylamide. So the deformability of the substrate is critical to this kind of behavior. And then finally, if you want to kind of get a temporal relationship, we can just do a cross correlation in time and say, well, given a displacement, a substrate displacement at time t, what are the odds of getting a velocity, a big velocity fluctuation at time t plus tau? And then just average this over all positions. And what we find is that basically the most important thing is that this correlation function across the zero lag time point, the slope is positive, which means that velocity fluctuations are always lagging behind deformation fluctuations. So you have deformation fluctuation, say at some point, and it's going to be sometime later that the velocity vector catches up with it. So and then you can like plot the slope of this as a function of, say, time in the experiment or density, and we see that indeed it's always positive and it decreases. So as the system slows down, velocity fluctuations are slower to catch up to deformation fluctuations. So I think the message of that is that cells are communicating long distance. They're contracting in a large scale manner, imposing a deformation field on the surface that acts as some kind of potential field for them to walk on and organize their motion. Now, how am I doing at time? Oh, excellent. Okay, so this next part of the talk is actually what I most wanted to show everybody, because I thought maybe I could get some help from you guys or some ideas, because it's something I'm still a little puzzled on, even though I really like the analysis. Basically, what are the cells doing on the small scale that give rise to all this? I mean, you can say, okay, there's this big deformation, and they follow it, but why do they follow it? And how do local contractions interact with, say, large-scale velocity fluctuations, or large-scale contractions interact with local velocity fluctuations, and these kinds of things? So it's a multi-scale and multi-time scale problem. And also, cell shape is really dynamic. It's not like you have a bunch of balls hitting each other and stuff. So basically, I attacked it with the only tool I can think of when you have to find like hidden structure in dynamics, which is basically a scattering method. I calculate the dynamic structure factor of cell motion and bead motion. And so just briefly, for those of you who aren't familiar with this, it's basically the Fourier transform of the density in space and time. Modulus squared of that gives you what's called the dynamic structure factor. And for any generalized hydrodynamics allows us to derive this for basically any system that has the right kind of memory kernel and all this. And point is that if you don't know what your fluid's doing, as long as it's stochastic, you'll usually get a dynamic structure factor that looks like this. And this omega of q, capital omega of q, defines a peak position, but we don't know how it depends on wave vector. And this gamma of q defines a peak width, but we don't know how it depends on wave vector. And so for fluids, we know how these things behave. This goes like omega over q, and this goes like q squared. Or rather, sorry, this goes like c times speed of sound times q, and this goes like q squared. But in our case, we just don't know, so we're going to derive that. And then just one final note: it's common to calculate the current version of this, the current correlation function, and it ends up just being omega squared times q squared times this, and it's the exact same thing. In either case, all we really want are the dispersion relations. The dispersion of peak position and dispersion relation to peak width. I know this doesn't sound like a good plan, but the reason you want this, is because you want to know what on some length scale is there a special, or rather, given a Fourier component, given some length scale, is there some special corresponding time scale, and what's the lifetime of that? And furthermore, are there a whole set of length scales and time scales that lead to propagation of things? And this will start to allow you to kind of tease out how these two densities are interacting. So here's a sample of a dynamic structure factor of cell motion. And then if you take a slice along here, you can fit the line shape with that function on the last curve, and the line shape fits beautifully. And so, like if you do it at one q value, you get like a peak here, and if you do another q value, you get like a peak there, and so forth. So you get a peak position and a peak width. Now, so what do these things look like? Well, for the cell layer, the peak position dispersion, so we have omega versus q, and it disperses like this, and the peak width goes like this. So the only reason I want to show these is to say one thing. this motion is underdamped. The peak position is higher than the peak width. Just barely, but it means that maybe density fluctuations can propagate a little bit. Not very far, but a little bit. And if you want to say get some propagation speed, you take the slope, and that's the group velocity of your fluctuation. The gel, however, is always overdamped. The peak width is always much larger than the peak position. So you can never get a propagating mode in the gel. But however, you still get fluctuations, and you get a frequency, and you get a lifetime from the peak width. And so these can all be useful. So if you do this for all of the data sets, they all look like this. The frequency goes down, etc. This is if you plot the gel dispersion on top of the cell dispersion, I think the first thing you see is that they cross at 2 points. And I think this is important because it says that there is a spatial wavelength in both and a spatial frequency in both that match up. Means you can get strong coupling there and there. And furthermore, I thought, well, maybe these all have similar shapes, so maybe these important length scales will allow us to rescale all the data and collapse it. And in fact, you can rescale all 16 data sets in the gel and on the cells, and you still preserve this kind of crossover and shape. And also, what's potentially interesting is there's an energy gap. It says that this mode needs a little kick to couple to this mode, and it makes me think maybe there's a way to change this energy gap and therefore change the properties of the system. And however, that's just I don't know what's that. Okay, this is second to last slide. I figure those length scales and time scales are important. So just to get a visual idea of what's going on, I take my data and I Fourier filter it and get rid of all wavelengths and frequencies except for the crossover. And so in the gel, you see basically what looks like just a couple fluctuating dots going like this. It's almost like an optical mode or something, or a standing wave where just like no speed, no propagation, and if you watch it long enough, you can convince yourself that each one of those little dots doesn't live for very long. But if you do the same thing on the cell layer, you actually do see little like wavelets that live long enough to propagate their own distance, and kind of all line up in these streams and stuff. So I think short wavelength fluctuations do propagate like waves, and all of the other fluctuations propagate, or rather don't propagate. They're all overdamped, and sometimes it just sits still. So finally, we want to figure out their relationships. So I just thought, well, let's just go back to a correlation function. Let's say I can take those Fourier filtered movies and say, given a long wavelength fluctuation in the substrate, how long till I see a short wavelength fluctuation in the cell layer, or vice versa, or basically there's 4 combinations. So you can do that, and I think there is a logical sequence that has to happen. You pick one and you just walk from one to the next, and it's if you want to answer the question, how do long wavelength deformations end up translating into long wavelength migrations via some local fluctuations? It follows a logical order based on how these correlation functions evolve. Long wavelength deformations excite short wavelength cell fluctuations. Short wavelength cell fluctuations excite short wavelength deformation fluctuations. Somehow, I don't know how, short wavelength deformation fluctuations give rise to long wavelength migrations. This is the part I'm totally fuzzy on. I don't know how to think of it. I'd rather have a model. I'm trying to do this in a model-free way, but I'd rather have a model to understand this. So if anybody is marginally interested or has an idea, please contact me and we'll write a paper. I'd love to. So thank you very much.
Anybody who wants to ask a brief question?
So in the first part of your talk, you showed the dependence of the correlation length on the density of the cells, and I guess you did it by just waiting, but while cells are dividing. Is that correct? On the substrate? Or?
Yeah. Throughout, so this is one really, really long experiment, and they're constantly dividing. But I chopped the data up into short enough data sets that I'm not dominated by.
My question was, how can you be sure that that is due to the density change and not maybe some extracellular matrix developing or cells are aging?
Yeah. No, that's a good point. I don't know. Our collaborators who did similar long time experiments like this stained for like fibronectin and things like and didn't see any kind of like large scale ordering or deposition. But I don't know. I mean that's totally possible. However, I'd have to say that it has to depend on the substrate because you see the opposite behavior on glass.
I mean, you can probably fix the cells so they don't divide, but you can squish them and
or you just prepare a new sample each time. Or something.
Any more questions?
Well, let's thank the speaker again. Next, we have the talk by Torsten Weller from Syracuse University, speaking on F-actin dynamics in human skin cells, directing the velocity of cell growth.
Anybody a Mac expert in getting this to display? No. Well, there's a thing is you're winning an entire corporation. No, I think you have enough guys who are anti-parallel at a certain distance.
Christina, there's a screen behind you. You have to click it out.